We're going to discuss two methods of super-resolution fluorescence microscopy in this tutorial. One is stimulated emission depletion, or STED, and the other one goes by many names. Here I'm going to stick to one, which is stochastic optical reconstruction microscopy, or STORM. It's also called PALM, or F-PALM. I'm going to start out by describing a little bit about each technique separately, and then I'll start drawing some parallels between the two of them. In stimulated emission depletion microscopy, you start off with the idea of hitting a XY region of interest with an excitation beam which is focused to the diffraction limit. And I will sketch that out by drawing a set of crosshairs and then sketching a blue beam, brightest in the middle, like if it was a Gaussian beam, and then something like that. That's just supposed to represent a nice Gaussian intensity beam, and I will label that as such. And if we were to hit an XY plane with this sort of beam coming down on it, what we would get, if I now draw a set of axes where the center of this excitation beam is some location here on an x-coordinate axis, say, and this axis here is the intensity. So I do a cross section of how much of this intensity profile. I might expect to see some fluorescence. I'll draw it in the green, and it might look something like this. So there's my cut through of the fluorescence coming off, being excited by this blue light. It comes off as green light. So this is fluorescence. The idea of stimulated emission depletion is that instead of just shining this one beam of blue light on the sample, you also shine on those same axes, which I'll now copy over here. You shine on a donut beam. A donut beam I will draw as best I can by hand here as some sort of beam that has a lot of intensity in a ring. It'll be brightest along some mid-region there that I'm trying to sketch in solid red, and it will have relatively little intensity in the middle. So that's our donut beam. I'll label that the donut profile beam, and it has a name. Instead of excitation beam, it's the depletion beam. That's the part of the name of this technique. And when that beam appears on top of the excitation beam, it sets up an intensity profile which has almost no intensity at the center of the blue beam. So we'll draw a very low amount of intensity there in red. And away from there, it has higher values. So it's got high values out there and high values out there. And eventually it will come down again. So that's the pattern that we've got set up over here. The important thing about this technique, which I'll explain more below, is that regions where we shine an intense depletion beam, like where the intensity is high here and here, it's going to suppress fluorescence emission. So even at these regions as we creep in towards the center, which I'll label with x-coordinate A, right at A, I'm going to get just about as much fluorescence as I would have without the depletion beam. But a little ways away from A, I'll choose some location coordinate here, like B. So there's the value at B. At B, there's enough red light that it's suppressing some of the fluorescence, and I'm not getting as much green light as I would have if the red light weren't there. Let me show you what the formula is for that. We've already talked in the course about the idea of a fluorescence quantum efficiency. We gave that the Greek variable phi, and we could say that the fluorescence quantum efficiency at some location in the plane of illumination, function of x and y. In general, we've learned that there's a certain decay rate due to fluorescence. We would call that k sub f. And then the denominator is going to be the sum of all the decay rates. So one of the decay rates is K sub F. Another decay rate, which might be quite small, so I'll write it as a small thing, would be K sub NR for non-radiative pathways, like collisions with the environment. And then the thing about STED is that you get a third term, which will give the value of K STED times an intensity-dependent term, which is the intensity at a location xy ratio to some reference intensity, some constant. And this expression here gives us the essence of what STED is accomplishing written mathematically. If you have a very low intensity somewhere, as you do at location A, the STED beam, the donut beam is very weak there, then this term here is small, and we have about the fluorescence quantum efficiency that we would in the absence of the red beam altogether. If, however, this term here is large, we can make it larger and larger as we increase the intensity of the beam more and more, and at locations where this term is large compared to K fluorescence, this becomes the dominant method of decaying from the excited state once a blue photon has been absorbed. So we could then deduce about what the fluorescence emission profile is going to look like. I'll draw it in black. At location A, it's going to have just about as much fluorescence as it would have before. But as I move away from location A, I'm going to have less fluorescence relative to the green curve because the red starts to cause there to be other ways of de-exciting the excited molecules. So that gives me a profile that looks something like this. So I have a narrower distribution in black than I did in green, and that's the essence of the super resolution of this technique. So if I were to write out in English what it is that we're doing here, I would say that we are telling molecules that are not right near the center of the excitation beam, we are telling them to choose a non-fluorescence decay path. And here's how I would write that out as a sentence. That we are compelling excited molecules that are away from the center, away from a chosen special spatial location. We're telling those molecules to choose a non-fluorescent decay. When I say that we are compelling excited molecules to choose a certain decay path, I mean that we are compelling them with this very high intensity to have a much higher rate constant for STED emission, something I'll explain in a second, compared to fluorescent emission. What does the energy diagram look like for this? We've drawn throughout the semester some Jablonski diagrams. So if I were to draw a ground electronic state with some vibrational levels and an excited electronic state with some vibrational levels, we've called this often the S0 and the S1 state. If we start out with the absorption of a blue photon up to somewhere in this vibrational manifold, and it relaxes down to here. If we, in situation A, where there is no STED beam, we could say that what's happening there is we're just sending in a blue photon onto the specimen, and what will come out in that situation will be, in situation A, location A, will be a green fluorescent photon. If, however, in a second scenario, which might be happening at location B, here we're also sending in a blue photon, but we're in addition sending in a very intense a beam of red light. We can crank that up as high as we want. Then instead of a green photon being emitted, as it was before, that might go down to this vibrational level, the red photons compel this to emit a red photon which doesn't go down to the same level. And so a different energy photon is given off. It's stimulated by this red beam to decay, giving off a red photon. That's the nature of stimulated emission, is the wavelength of the stimulating beam drives the emission of a photon at that very color. So in situation B, it's much more likely to get a red emitted photon than a green one. And that is why at location B, you have less green light than you would have otherwise. The way you build up an image in this situation, the way we gain our super resolution here is that we have a beam and the location of the beam center. That is something that you control in this experiment. You know where that beam center is because you've designed your optical system to point at a certain location, and that's something you can engineer to know with high precision. You can only focus the excitation beam to within a diffraction limited spot size, but you know where the center of the excitation beam is with higher precision than that. And if you can move it slightly, and you know where the center of that beam is with higher precision than the diameter of an excitation beam. You then can build up an image which is built from raster scanning the beam. And the last thing I'll say about super resolution from STED is that what is the biggest pitfall of cranking up the intensity? Because you might think, as long as I have a true zero here at A, I want to crank this red beam up as strongly as possible to make almost very close B locations still be strongly stimulated down to emit red photons rather than green ones. But there is a limitation, because if you have very high intensity very close to the center of the beam at location B, then out here at the peak of the donut beam, here, at that peak, you have a very high intensity, and it will be hitting molecules and it can destroy them. And the term we'll often say for that is that it can bleach them. It can place them into electronic states that are different from the ground and excited here, some place where it's stuck and it doesn't absorb light anymore, so you can't make it fluoresce. So bleaching is the biggest downside. All right, let's look at stochastic optical reconstruction microscopy and explore how that's different. Let's imagine a sample plane where there are 3 individual molecules that are capable of fluorescing. So I'll draw this little sample plane here. So imagine you're just looking at the sample plane. And now, as we move forward in time, we are going to hit this with a dim activation pulse. And what I mean by that is that in this same field of view now, a little time later, it's dim enough that most of the molecules in the sample plane don't absorb any light at all. They don't absorb even a single photon of light. And so of our 3 molecules, 2 of them are going to stay exactly in the state they were in. They haven't absorbed anything. But this dim activation pulse, consisting of individual quanta, at one location, and I'll draw it as an open green circle with a little hash in the middle, that one location has become activated. And what I mean by that, and I'll explain it more below, is that that location has gone from being unable to be excited by the blue light to fluoresce to being in a state where it can be excited by blue light it can be absorbed and then can give off a fluorescent photon. So two of these molecules are simply in what we call a dark state, unable to absorb an excitation photon, but one of them is able to. So now, if we come along sequentially with an excitation beam, and we look at what's happening in the sample plane after that, we now have two locations of the two quiet molecules where we get no light at all. I'll mark those with X's. But then at the center, centered on the activated molecule, I'm going to get lots of emitted light. I'm going to now be thinking about this as if I'm looking now at the detector plane. So think of this plane as containing pixels of a CCD or a CMOS array that I'm actually registering counts at. I am going to get light, some of it very much right where the activated molecule actually is, but because this is an optical system, I cannot image that any more precisely than to have an airy disk, a diffraction limited spot here. So here's a whole bunch of places where there's emitted light. And I meant to draw it in green, so I'm going to redraw it in green. So here, at the proper color for fluorescence in this tutorial is a diffraction limited spot of green light. The parallel with the previous case is that although I have a diffraction limited spot of green light, because it's the only molecule in the neighborhood that's emitting, I know, because I chose my light to be dim enough, that I expect only one molecule to be emitting. And so when I see a spot, I can walk up to it and I can calculate where the center of it is. So I put a little cross there, and that's the location of the center. And just as in the STED case, I have arranged my beam scanning optics so that I know where the location of the beam center is with high precision as I raster scan it. Here, I take an image of this plane, and I have many emitted photons from that activated fluorophore, so I can calculate the center of that spot very accurately. I can assign the molecule to being where the red cross is. If I were to say this in English to match this sentence here, what I would say is that we only allow a few isolated molecules, one of which we saw here. We only allow a few isolated molecules at, instead of a chosen spatial location, now we are having it be at a chosen time interval. The exposure time for this one frame that we've gathered, we're going to only allow a few molecules during this time interval to be eligible to be excited at all. So only a few molecules at this interval were only allowed to be excited in an excitable state at all. The verbs here can be a little confusing. Remember that we have an activation pulse and an excitation pulse beam. So one molecule has been activated. It now is a candidate for being excited if it absorbs an excitation photon. What does the energy diagram look like here? The concept is that you can start out in some sort of ground electronic state, and we'll call that the dark state. That's where all three of these molecules begin. When you absorb the excitation pulse, it makes a transition. It's not necessarily going up or down. I'm going to draw it as a somewhat upward arrow. And you can simply transition to a different configuration of the fluorescent molecule. And for reasons we don't have to get into, and that honestly I can't get you into, it now transitions to being in an excitable state. The excitable state is capable, if we have an upper state up here, it is capable of absorbing a blue photon and emitting a green photon to somewhere. And going through this cycle n times, where n is the number of photons that I collect from that fluorophore before eventually something ends the process, it gets stuck somewhere and you get a certain number of photons out, and the storm gets better and better the more cycles you can put it through, because you can calculate the center better and better. What's the parallel to this statement about how you get location accurately? In this case, it's really that we're figuring out where single molecules are. So because we know that this cloud has been caused by emission from a single fluorophore, that's what's giving us our super resolution. We have this incredibly small light source here, way smaller than the diffraction limit of focusing light. We have only a single molecule emitting light. So, and we're able to tell it where it is more accurately than we can squeeze a focused beam of light down to. We can get its center very accurately. So the answer is that single molecules, in this case, they are assigned through the data. They're assigned to XY locations, and that's what's done with high precision. You can't just excite this fluorophore once, then you'll just get one dot somewhere in the neighborhood of where the molecule actually is. But if you do it n times, and n is in the hundreds or the low thousands, you can get a cloud where you converge much more accurately on where the molecule truly is, and then you can make a cross there. How do we build up images in this case? Images in STORM are constructed by adding together many frames like this. You make a few red crosses in the first frame, a few more in the next frame. So if you add together many sparse images, you then build up a composite image with lots and lots of plus signs in it, and all those plus signs together will tell you where all the molecules in the image are, and that's what forms the fluorescent image that you wanted with molecular resolution for each one of the crosses. And you can then get images that beat the diffraction limit because you're no longer constrained by diffraction in assigning where the molecules are. Lastly, what's the corresponding pitfall? In the case of STORM, you've got to be careful that you don't make your activation pulse too bright. If you get greedy and want to have lots of activated molecules in your field of view all fluorescing at once, you might activate neighbors with too high a probability. In other words, you'll activate them too often. And the problem with that is if you have one green cloud and another green cloud right next to it, very close by, you will not be able to tell that there are two different molecules there. You'll think that this is just one big cloud of data, and you'll mistakenly interpret this as only corresponding to one molecule, and because there's two slightly off center, you're going to place the cross in the wrong place, and that blurs out your resolution. So STORM requires you to only activate a few so that it's very unlikely that you're going to have two neighbors within an area disk of each other glowing at the same time.